Can I request all of you to kindly fill up the Google form that I have given as a feedback? Those of you who are present right now, just click on that and fill it up. Just 2 or 3 questions to be filled up.
Ma'am, we'll wait for another 5 minutes.
Yeah, yes.
Oh, okay.
Till the students come, we should be waiting actually.
Yeah, ma'am. Yeah.
Because it's a hectic day for them.
Yeah, throughout the day, they have to spend in front of the mobile. Ma'am, we have arranged around 7 different halls.
Okay.
They have to sit in those
respective halls. They have to listen.
Oh, they are in the college campus or what?
Yes, ma'am.
They are under supervision of faculty members, sir.
I see. Actually, I didn't know that.
And also, we have arranged one seminar hall, and there we have make a projection of the this workshop.
100
I see. That's still better, so that they can see properly. Every room has a projection.
No, madam.
Only two.
Okay. And the others, they are seeing through their mobile.
Mobile, and some of them they are using laptop and all, madam.
Okay. So that's good. So you have all provisions, and children are coming to college because now it is open.
Yeah, madam.
Okay. Good.
And
Sir,
that's why the number is less, madam. And most of the students, they are watching in the projection.
Projection.
That's
okay.
what.
Never mind. As long as they see and learn, it is enough.
Yeah.
Number doesn't matter.
And all 2 sessions are very nice, ma'am. Thank you so much.
Welcome. Sir, your name, please.
Ma'am, myself Santosh Gorpade, assistant professor in physics department, ma'am.
Okay. So how many teachers are there in physics?
15 numbers.
15, madam. 15 number.
15. Oh God, a huge department.
15, ma'am.
15, yes.
15.
It's a huge department, yes. Actually, teaching the children front so that you can see what mistakes they are doing, correct them, is much easier.
Yeah.
Now I cannot make out what they are doing.
Yeah.
Yeah.
By their response only we see, madam. They are active participants. All are.
And they are writing IA, ma'am. That's why I have not sent that handout. They are unable to read and come. That's why they are
Okay.
Otherwise,
What we can do
all are very active.
Yeah, no, for the Excel sheet, we can have one full day. They sit down with the laptop and do it along with me. Then only they will understand better.
See, ma'am, whether I can arrange it or not, because laptop means I have to think
No,
over
a handful of them, 10, 20 of them also, if they are interested, we can have it for them. They can teach their friends.
We can make it.
Yeah. So 10, 20 people are there, we'll teach them and then they can teach their friends.
Yes, ma'am. That we can.
All graph making, all that will be useful for them.
It will be like hands-on training, ma'am.
Yeah, that's right. That's right. Actually, that's how I've been doing all this while. Only after pandemic started, I'm doing it like this.
Online.
This is difficult for the children to understand and immediately grasp. It is difficult. They should actually practice it along with me.
Yeah, madam. The spreadsheet was interesting, madam. So many of the students they can take advantage of it because it's very simple, but they are unaware of it, madam.
Yeah, that's it. I mean, it is very simple actually.
Because they bore about the drawing the graph in the graph sheet, madam. Once they are familiar about this Excel, they can have a more interest.
Now,
about
all these colleges, schools, they are allowing Excel to use it for your graph calculation and all other calculations. They are using it.
Madam.
So it will be good if they can also practice and learn.
Yeah, the error is less, madam, there in the Excel sheet. But while they're drawing manually,
error is not less, but then they can do it quickly, so that they don't have to spend too much of time drawing graph. Drawing graph, they have learned it in class 9, 10, 11.
8, 9,
Why
10.
should they spend so much of time in drawing?
Yeah, madam.
That is my idea. And lots of other things can be done with the Excel.
Madam.
I'm using it very for a variety of reasons. So they should see that and pick it up.
Yeah, madam. Yeah, madam. Ma'am, at the end, our faculty member also interact with you, madam. We have some time for interaction.
Yeah, no problem. And anybody.
Yes, madam. Our faculty members, they may also interact.
Yes.
Yes.
Sir, I have given a feedback form for the morning session. I want the children to fill it up. Could you kindly give them instructions? They can simply click on that and 2-3 questions are there. They will fill it up. Yes, no, that's all.
They are familiar, madam. They are familiar with this Google form.
Okay.
They are familiar.
Just request that I have put it in the chat box. They can click and fill it up.
Yeah, madam. Yeah. Shall we start, madam? About 9:40, 94, 97 are there?
There. Yeah, no problem.
We'll begin.
Good evening, ma'am.
Good evening.
Let's get into the last session of this workshop. Ma'am, now you can start the session on virtual lab. Over to you, ma'am.
Yeah, thanks a lot, Bhavani. So we will start with the virtual lab. Now, before what is virtual lab, let me make it clear. Are you in college and are you going to the lab and doing experiments? Yes or no? Please put in your chat box. Are you doing any experiments in the laboratory? Yes, you are doing it. I'm just asking you, in between, the college was closed for a long time last year. Did you do any lab or you simply gave the exam based on some values? But you all didn't have any exam. I think practical exam was not there. So you escaped. But how did you do the lab last year? How did you do the lab? I'm not sure, but in our college, I was teaching in Maharani Lakshmi Amani College. In our college, what they did, since the college was closed for a long time, only few experiments, values were given to them. Values the teacher had done, they put it up in the thing, WhatsApp message and all that, and asked them to plot a graph and submit it. So that is how the experiment was done. But that is really not an experiment because you are simply taking somebody else's values and you are entering it. So during such time, how do you actually do an experiment is what is known as a virtual lab. You can actually do the experiments like in a laboratory, but without any presence of apparatus. All the apparatus, everything is there on the internet. You will have to take it, change, make the arrangements, connections, etc. Whatever you have to do, you can click, and then suppose you want to take a graph of potential versus current. Then you have to change the potential, note down the current, and then plot a graph. That is called a virtual lab. Now, why it is important is, suppose you have your final exam and you are not allowed to go to the college and practice. If you can't practice, then you are not sure how well you will do it for the exam. If you want to practice it at home, you can sit at home and practice. You can learn all the variety of things, possibilities that is there. In the lab, you have just 3 hours. In that 3 hours, a teacher tells you, okay, do this experiment, plot the graph, show the graph and go. So you are learning very limited things. But if you have a virtual lab facility, then you can do all the different things that you can change. For example, you did V as to I in the lab. But what will happen if your R changes, I remains a constant? What will happen if the power supply or the EMF of the battery changes? What will happen if the temperature changes? All those different factors can be done at home, sitting at home without any apparatus, and still you will get perfect values because that facility is there in the VLab. That is why it is important for you to learn how to use a VLab. And once you learn how to use a VLab, there are so many different labs, places where you can go and collect all these experiments. You can go to the internet, search for that, whichever experiment you want to do, and you will connect yourself. So today what I plan to do is, we will do an experiment on photoelectric effect. Why photoelectric effect? Because 2021, okay, is the year when Einstein got his Nobel Prize, and it is 100 years. So all of us are celebrating Einstein's receiving the Nobel Prize in 1921, because this is the 100th year, and he got the Nobel Prize for photoelectric effect. Therefore, I would like to talk to you about photoelectric effect. And I'm sure you have heard about photoelectric effect in your second PUC classes. Do you remember what is photoelectric effect? Can anybody tell me what is photoelectric effect, or write in the chat box? Any one of you, write on the chat box what you know about photoelectric effect. Yes, please. Whoever knows, second PUC you have done, you just write photoelectric effect is this. 2 minutes, 2 lines. I want you to do the ejection of electrons. Excellent. When will the electrons get ejected? Under what conditions? When light strikes a metal. Wonderful. When light strikes a metal, electrons will get ejected. So how will I study electrons ejecting? Can you see the electrons? Yes, metals. Very good. Can you see the electron? Yes or no? No, we can't see the electron. Then how will I know that when light strikes the metal, electrons are coming out? So I must have some other device. How can I check the presence of electrons, somebody? Electrons are negatively charged particles. It is not visible to us. So how will I know that electrons are there? Any suggestion? Use its property and suggest. Electrofoil, okay? Electrofoil is one way. If you keep a metallic foil, then electrons will go and strike that metallic foil. If there are 2 foils very close to each other, they will get repelled, because negative repels. By looking at the repulsion, you can find out that yes, there are some negative charges over here or positive charges. Very good. Electrolysis. Somebody else is saying electrolysis. Electrolysis is a liquid when it splits up into its ions. So if one of the ions is an electron, that electron will go towards the positive plate, and then there will be a current flowing. If you have a circuit, complete circuit, then current will flow, and you can find out that yes, current is flowing because of electrons. Therefore, you can check. Very good. Any other? One more? 2 good ways you have told. Can I find out if electrons are moving? What else? Yes, one more choice. What happens when a charged particle goes? I will not suggest, you tell me. You tell me. 2 choices you have given and very beautiful choices. Now I want somebody else to answer. If there are electrons, how will I check? E is equivalent to HF. No, that I cannot find out electrons or not. You are telling me that the energy of the radiation that is falling upon the metal is equivalent to HF. Ballistic galvanometer, wonderful. Ballistic galvanometer, also presence of charges can be gauged. Yes, wonderful. BG. Very good. Keep it up. Nadaf. Excellent. Electrons, when they flow in a circuit, they will produce current. If I put an ammeter, I will know what is the current. So from the current itself, I can find out that yes, electrons, this much electron is flowing for this much time, etc., etc. So I'm now going to show you a small simulation of photoelectric effect. Once you are satisfied with that, then we'll go to the virtual lab. Okay, so virtual lab you should understand. Therefore, I will show you first what is happening. I hope I can share it with you. What happened? Yeah. Yeah. Now have a look at this. Yeah. Look at this. Here is a simulation of a photoelectric effect. What is photoelectric effect? Now, whenever you have a metal, if you allow radiation to fall upon the metal, if the energy of this radiation is large enough, then it will produce electrons. These electrons, when they are produced, are negatively charged. So if you have a positive charge over here, the electrons will move towards it. And if this is connected to a battery, to make it positive or negative, suppose I connect over here negative and over here positive, this will become positive, this will become negative. If I put one current meter over here, how much electrons are passing through that ammeter? The current will be noted over here, and therefore I can say that yes, electrons are passing. Okay, so that is a simulation over here. This simulation has been done by Colorado University and it is called PhET simulations. Whenever you have time, go and see all these PhET simulations of Colorado University. There are many of them and they will teach you physics very nicely. I'm just showing you over here. Now I'm saying when light falls upon this metal, the metal is producing electrons. Under what conditions? I'm just showing it to you now. Okay. If I make the intensity something, whatever it is, how much intensity of the light? 13%. If I make this frequency of the light smaller, 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 and smaller. Can you see that very few electrons are coming? So the amount of electrons or the energy of the electrons depends upon the frequency. If I make it smaller, the electrons that are coming is lesser energetic. If I make it stronger, this is negative potential. That's why it is not behaving like this. I'm sorry, I will make it 0 first. Okay, I made it positive, so it is easier for you to see. Okay, now see, electrons are moving. They are going towards the positive plate. If this was 524 nanometer, green in color. Therefore, I have a green light. Now, if I decrease it and make it blue light, then what happens? No current. There is no electrons. So there is a minimum frequency below which it will not come, above which it will definitely come. So if I have yellow thing, frequency is more. Look at the electrons, how fast they are moving. I will also change the intensity and show you what is happening. It is not responding quickly. I don't know what's wrong. Yeah. Now I have intensity which is 30%. Look at the electrons. I will make the electron intensity still more. More number of electrons are coming. See, I'm going to make it still more. Even more number of electrons are coming. So when I'm going to change the intensity, the number of electrons that are coming out from the metallic plate will increase. Okay, now I'm keeping the intensity as it is, and I'm going to change something else. Suppose I change the current, I mean voltage. It was 1.8, I made it 3.2. Look at that. What is happening? The electrons are moving with faster kinetic energy. They are moving faster. If I make it still more, instead of 4.8, look at the electron. It is running. It's not going slowly, it is running. If I make it a little more, 5.2, the speed will increase still more. So the kinetic energy with which the electrons are moving is going to increase when the positive potential is increasing. Therefore, it is going faster and faster and faster. All this while I was changing the voltage and I was making it positive. Now what will happen when I make it negative? Just see what I'm doing. Now it is 0. I made it -2. The electrons had some kinetic energy, but if it is not sufficient, they will not go to the positive plate. This electron is going away. Can you see? If the kinetic energy of the electron is not enough, it will go back to the plate. Only those electrons which have large kinetic energy will come towards the positive plate. If I increase it still more, made it -2, now see what has happened. All the electrons are going back to the metal plate. They are not going to go to the positive plate. They came out, had very little energy, therefore they are going back. Can you see over here? They are coming out, very small kinetic energy, they are going back. So this is said as this potential difference between this and this, which is recorded over here, is larger than the stopping potential. Therefore, the electrons are not coming towards the positive plate. They are getting reflected. If I do it slowly from -0, just see, no electrons will go at a particular value. I will first make it go. Then now let them go, then I will tell you. Now I'm making it positive so that the electrons will reach the plate. Then I will make it negative. Now I'm making it negative. When it just stops, I'm making it negative. Some electrons are going. Some electrons are going. Now no electrons are going. So this potential, which is -1.4 for wavelength equivalent to 494 nanometers and intensity equivalent to 36%, is the stopping potential for this particular wavelength. That means this is defined for this particular frequency. If I change the frequency, wavelength, and make it larger, then no electrons will come. If I make it smaller, then some electrons are coming closer. Let me keep it over here. Still the electrons are not able to come because it doesn't have sufficient kinetic energy. It is coming little more distance and still it is going back. When I'm making the wavelength still smaller, it is coming a little larger distance and still it is going back. So for different frequencies, it has stopping potential, which is different. Okay. This negative potential that I have put over here is the corresponding stopping potential, which prevents the electron from going to this plate, which we can study in our laboratory. Okay. I hope you have understood what I'm doing over here. I'm changing the wavelength of light. I'm changing the potential over here. When the potential changes, the current also changes. When it is stopping potential, current will be 0. But when I make the potential larger, positive, there will be current. Okay. So I can note down what is this current. I can note down what is this potential. I can note down what is the corresponding either frequency or wavelength. I can also note down what is the intensity. So there are 4 variables over here which will change. What are the variables? Intensity can change, wavelength of frequency can change, voltage can change, current can change. So how two things are changing with respect to other two things which are constant, we do it in an experiment to find out the nature of the graph. I'm just showing you the nature of the graph, but I want you to plot it. So here what is happening, it is showing you by the dot. If I keep changing it, then it will plot. Can you see? I'm changing it, it is plotting. So the current, when it was negative voltage, this is negative voltage, this is positive voltage. Negative, it gradually decreased, became 0. But in positive, it slightly increased and became steady. It became. This is a graph of potential versus current. So this type of graph, if you draw, you can understand what is happening to the voltage, what is happening to the current, for which frequency, etc., etc. You can study. I have plotted over here a graph of current versus battery voltage. I can do it for other things. Show only the highest energy electrons. Where did it go? Anyway, so current versus light intensity. Suppose I want to draw. Now look at this. Current versus intensity means I should change the current and with the intensity. Look at the current now. It is showing 0.0150881 for different intensity. Now it is plotting for different intensities. Intensity is decreasing. What is happening to the current? The current is also decreasing. If I increase the intensity, how will the current increase? That also we can plot a graph and see. We are increasing. The current is also increasing like a straight line. So this straight line graph tells me how the current will change with respect to the intensity. Let me now show something else. Let me say I want to plot electron energy with respect to frequency. So what will happen? This is your frequency and the corresponding electron energy is nothing but the voltage, the stopping potential. So I will make this stopping potential change with respect to frequency. Please see. No, this is too high. I'm now changing with respect to frequency. I'm going increasing the frequency, decreasing the wavelength. See how it is drawing. Okay, so this is the graph of the corresponding kinetic energy of the electron with respect to the frequency. It did not start from 0, 0. It started from some value over here and then it was a straight line. All these factors will tell us about photoelectric effect. But how will you, this is a simulator. It is actually simulating by simply moving this voltage. But this is no experiment. This is only telling us that this is how it will behave. I want you to do the experiment. So for doing the experiment, where will I do? I can't do it in PhET simulator. I have to go to the VLab. So this is a VLab which is available in the net free of cost. For students, it is called Value at Amrita. When you want to go and use any VLab, open your Google Drive and write over here VLab's photoelectricity. Can you see my screen? Yes or no? Can you see my screen?
Yes, ma'am.
Yeah, okay, very good. Because only if you can see, I will tell you, otherwise it will be difficult for you to see. So now what I'm showing is, if you want to chat, I will take it this side. Okay. If you want to go to a VLab, you can enter over here, VLabs, what experiment you want to do. I did electricity. So you will get all this. Please look at vlab.amrita.edu. It is one free place where you will get all these virtual labs, whatever you want in one thing, umbrella. I want photoelectric effect, therefore I can click on this and then it will come. Or I can go to home page, photoelectric effect, virtual labs, click on this and I will go to. I have already clicked it and I have come over here. Okay. So when you want photoelectric effect, it will show you the apparatus of photoelectric effect. Now, how will I do the experiment in photoelectric effect? I will tell you before. How will you go to this apparatus? It will ask you, please log in as a guest or as a faculty. You can't do it as a faculty because your college has to take the permission for giving it to you as a thing, using it regularly. You can go as a guest. In fact, I have joined as a guest. When you go as a guest, it will give you, ask your password, ask your ID, etc. You will fill it up. Then if you press OK, it will take you as a guest. Once it goes to the guest format, then you can go to the lab. And this is a particular lab which is telling you that these are the apparatus with the help of which you can do photoelectric effect. Now, what are the apparatus? I told you that light has to come and fall upon the metal. This is a photo tube. A photo tube has one metal plate and it has another plate which can be connected to the positive of the battery or negative of the battery. So this plate on which light falls is coming from here. How do I know that light is coming from here? I can show it to you when I switch on the light. Okay, I switched on the light. Can you see one light cone is coming and falling over here? This is the light cone which is falling on this plate over here, and it is going into this tube. There is a metal plate over here. It is going and falling over there. Now that metal plate should be connected to the power supply. So for this positive is connected to the positive over here. Negative terminal is already connected to the negative terminal over here. The reading over here is telling me 0.00 voltage. How can I change the voltage? I will show it to you. You can change the voltage and then change the current also. I will show it to you. This is the voltage applied. This was showing 0. Please see, if I move this, it is becoming 0.6, 0.7, minus 0.8. That means it is connected to the negative potential. Negative potential means the cathode is connected to positive and the other plate is connected to negative. Therefore, the potential will always be negative. We want to study about the kinetic energy of the electron, which is measured by negative potential. Therefore, it is connected in the negative potential for you to measure the kinetic energy. And how much is kinetic energy? Kinetic energy is proportional to the potential. When I say that the potential is 0.3, kinetic energy of the electron is proportional to 0.3. Negative sign, it is measuring the potential and kinetic energy, and the value, it is saying it is proportional. Exactly, if you want to calculate, kinetic energy is equivalent to E times V, where E is the electron charge, 1.6 10 to the power minus 19 coulomb, multiplied by 0.3 will give you the potential energy in energy units. But if you simply want to say how much it is proportional to V. Okay, so that I can now change this potential whenever you want in the experiment. Look at me, I'm just simply moving it up and down and the potential is changing from 0 to minus 10. I don't want to change the potential. I want to change the color of the light. Whether it was blue light or red light or whatever it is, I can change the frequency or the wavelength. Here it is marked as wavelength, 100 nanometers. I can make it 122, 134, 150, 160, etc., etc., 200, 300, 400, 500, and so on. Maximum it goes up to 750. So all the colors that you require can be got by the position where I keep this button so that the wavelength of light changes. Okay, let me first keep it at 100. Now, where will I measure the current? This is your current meter. This is showing that the positive of the current meter is connected over here, negative is connected over here, and there is a circuitry over here which is telling that the current is connected in series with the voltage. So that current I can measure over here. What is the unit of the current? It is written over here very clearly. The unit is in microampere. Very small current passes. So that current can be measured in microammeter. So I have a current meter, I have a voltage which can change. I also have a wavelength which can change. What about the intensity? Intensity also can be changed. It is given over here. Intensity of the light. Whether the light is very powerful, not very powerful, can be changed over here by changing the intensity of the light. Now it is at 5 milliwatt per meter squared. I can make it a move ray. 1 minute. Why it is, oh, this is 100. This is 0. It is not moving. I will make it -2. Then intensity I want to change. Now see, 5, 15, 20, 25, 30, etc. So I can keep it at any place I want depending upon the intensity that I require. Now in the lab, when you are doing this experiment, you don't have so much facility. In the laboratory, when you do, your teacher will tell you, note down the current for different potential. So change this knob over here, change the potential, note down the current, draw the graph and go. But here in virtual lab, look at the amount of facilities. I can change the wavelength of light. In college, you will have one thing, laser light, which is red, nothing else. So you can do with red light. If you have a green laser light, you will use green light. You don't have the facility to choose, but here you can choose everything. Another important thing that you can choose is the area of the plate. Look at that. This plate over here, if it has 1.1 centimeters squared, what will happen? If I make it 0.2 centimeters squared, what will happen? I move. Okay, now go to 0.3, what will happen? Go to 0.4, what is happening? Go to 0.5, what is happening? Everything you can change, but whenever you are doing an experiment, the best way is whatever can be changed should not change everything together. You should keep certain things constant and change only one variable, note the other variable. Now I will do one experiment with you. I kept the intensity at 5 watt per meter squared. I kept the area of the plate 0.1 centimeters squared. I'm going to change the voltage for a particular wavelength. I kept the wavelength at 100 nanometers. In your paper, please write wavelength of light is this much, intensity of light is this much, area of the plate is this much. First, write it down. That means you are keeping 3 things constant. Only the 4th and 5th thing you will change, and you will change one and see how the other one is changing. So now I want you to take down the readings. Then only you can plot the graph and do the experiment. Next time I will not change. You will go to this site. You will change and do the experiment all by yourself. Then only you will know that, okay, this experiment can be done like this. This experiment has to be done like that. You first read the theory a little bit. Go to the thing site. Go to the corresponding experiment, check what all is given, how to switch on, and all that will be written over here. Reset is given over here. If I have done one experiment, I want to go back to the beginning state, then I will reset. Okay, and switch off the light. When I don't want the experiment, it is over, I switched off. The moment I switch off this, everything else is off. This is off, this is off. That means the experiment is shut down. For doing the experiment, I have to switch on and then only take the experiment. Okay, now please write wavelength is 100 nanometers. I will keep it constant. Write down intensity is equivalent to 5 watt per meter squared. I will keep it a constant. Write down area of the plate is 0.1 centimeter squared. I will keep it a constant. I will simply change the voltage and then I will ask you to note down the current. When the voltage is equivalent to 0, you can see over here. You can see over here and you can note down the current. So when the voltage is equivalent to 0, how much is the current? You make 2 tabular columns. One is for voltage, one is for current. Are you doing it? Write the unit of current, write the unit of voltage. Only if you do, you will learn. If I do nothing, you will learn. I will only learn, you won't learn anything. Okay, did you write for voltage equivalent to 0? What is the current? Write it down. 3.86. Okay, so 0, 3.86. So in the current column, you write the unit microampere. In the voltage column, write the unit voltage. After having done, I will change the voltage. How I'm changing, you see, I am going to 0.7 is too much. I don't want 0.7. So I will go to small value, 0.4. Now write the voltage is equivalent to minus 0.4. Now what is the current? 3.66. So this is what is happening. When the voltage is increasing in the negative direction, the current is decreasing. From 3.86, it became 3.66. You have written it once, so you may not have understood what is happening. Next, I will go to 0.9. I need not jump in equal steps because I have to draw a graph. I can from the graph understand what is happening. I don't have to do it 0.4, 0.8, 1.2, 1.6 equal steps, not necessary. So I'm now going to take the reading for minus 0.9. What is the current voltage? 3.41 microampere. Are you writing with me? Yes or no? Because if you don't do, you cannot learn, I told you. Yes, you are writing or not writing? Yes or no, please write. Yes, yes, yes. Okay, very good. So now I have to decrease this and increase this because I'm using the same board. Okay, now I'm changing the voltage. I made it no to 1.7. I don't want to jump so high. So little I want to move. Now the next reading is 1.3. What is the thing current? It is 3.21. Okay, please write it down. Next, no, too much. I don't want to move like this. Yeah, minus 2.0. What is the current? 2.86. Whatever reading is written over here, same reading is written over here. You can take any one place. I am looking over here and changing this slowly. This is minus 2.6. The current is 2.56. Then I will go to minus 3.4. Current is equivalent to 2.16. Then I will go over here. I'm going a little fast because it's taking too long. Minus 4.7. Current is 1.51. Please write along with me. Then the current is minus 5.9. I'm sorry, voltage is 5.9. Current is 0.91, 0.91. I'm coming to small currents. So now I have voltage is 6.6, current is 0.56. Then it is minus 7. Please see what is happening. Minus 7.5, current has become so small, 0.11. Now I want it to become 0. Look at the current. It is 0. So this value, I think it is a little before that. I will check it. 8.1 also, it is 0. 7.7. I'm going to the value minus 7.9. It is equal to 0. Okay. For that voltage, when the current becomes equivalent to 0, is known as the stopping potential. So what is the stopping potential for a wavelength equivalent to 100 nanometers? If I ask you, wavelength was equivalent to 100 nanometers. What is the stopping potential? The stopping potential is equivalent to minus 7.8 volt. This from the graph also you can calculate and see. I'll give you 5 minutes. On the y-axis, on the x-axis, you write voltage. Negative voltage you don't have to write. You can simply write positive. So 0, 0.4, 0.9, 1.3, you take equal axis. 1 centimeter, 2 centimeter, up to 8 centimeters, 8 voltage, and plot it with the corresponding current on the y-axis. Plot voltage on the x-axis, current on the y-axis of all these values and tell me what is the graph like. Because until and unless you do, this is called experiment. You are experimenting, finding out for a constant wavelength, constant intensity, constant area of the cathode, how it does the voltage change with respect to the current. From that graph, I will tell you many more things. So I want you to plot it and then show me quickly. Who can do it? Everybody can do. Who will do it first? I want you to please do it and show. Tell me what sort of a graph, like how in the morning you did. Take a graph. For this, you take a graph paper better. Have you brought graph papers? Did ma'am tell you to bring graph paper?
Yes, ma'am.
Okay.
Ma'am was told.
Now, can you take one graph paper? X-axis voltage, y-axis current. Okay, current on the y-axis, voltage on the x-axis. Plot and tell me what is the graph like. And I want you to tell me seriously. I don't want you to bluff. I have drawn the graph, an estimate of the graph. I don't have a graph paper. I don't want to draw it in the graph paper, but I know how it will look. So in my estimation, I plotted the graph and I know what is the graph looking like. I want you to tell me what the graph is looking like. Or show it to me. You can make your videos on and the show. Or plot it in the chat box. Plotting may be difficult. I don't think there is line facility in the chat. Chat only writing is possible. I'm giving you some time and I want you to plot. So I'm doing a virtual lab work in the laboratory without any apparatus at home. I'm sitting at home and I'm doing photoelectric effect ka experiment. Who has plotted? Just do an estimate. You don't have to draw very accurately. Instead of 3.86, you can say 3.8, 3.6, 3.4, 3.2, 2.8, 2.6, 2.1, like that. Round it off to one decimal place and plot it quickly. Don't take too much of time. Decreasing in a slant line, ma'am. Wonderful. Shraddha is beautiful. Is it touching the x-axis somewhere? Beautiful. You've told it. Shraddha has done the experiment. Now, is the graph touching the x-axis somewhere? At 7.9. What is that 7.9? Wherever the current becomes equivalent to 0, the voltage, corresponding voltage is known as the stopping potential. So if I ask you, what is the stopping potential for this wavelength 100 nanometer? What will your answer be? What is your answer? 7.9. Suppose I ask you, for this wavelength of 100 nanometer, when the voltage was equivalent to 0, was the current 0? Yes or no? When the voltage was equivalent to 0, what was the current? The current was not equivalent to 0. What was the current? It was 3.86. So many details you have found out from the graph. Okay, and I'm glad you are able to tell. I'm watching your chat box and telling that you have understood this. Now we saw that for 100, the stopping potential was minus 7.9. I will not change the stopping potential. I'll just change the wavelength. Is the stopping potential 7.9? Maybe, because it is still showing current 0. Still showing current 0. Still showing current 0. Still showing current 0. That means for all wavelengths, the stopping potential is definitely less than 7.9. That is why it is showing me for all wavelengths, right from the beginning to the last. Now I want to find out what exactly is the stopping potential for a wavelength equivalent to 150. So what I will do, I will start the current voltage graph for the wavelength equivalent to 150. So now you write down in your notebook, when the wavelength is 150 nanometer, same intensity, same area, not changing. I simply want to study voltage and current. Now look at this. When the voltage is equivalent to 0, how much is the current? How much is the current? 1.79. So voltage is 0, 1.79. For 100 nanometer, was it 1.79 or more? You had told me that it was 3.86. So immediately when the wavelength is increasing, the first voltage for first current when the voltage is equivalent to 0 is also decreasing. When the wavelength is increasing, the current is decreasing. Is it becoming clear? Because you got 1.79 now. Previously you were getting 3.86. Now let us check this graph. Is the graph of the same nature. I'm just writing for 1.5 volt. What was the current? 1.04. I'm jumping big steps because I want to do many things now. For minus 2.7 volt, current is 0.44. Again, current is decreasing when the voltage is increasing. No, I'm going too fast. When it is minus 3.1, the voltage is 0.24. Now I'm going slowly. Oh, it's becoming zero quickly. Zero quickly. When it is becoming 0.4. Okay, 3.6, it is 0. Therefore, minus 3.6, the current is equivalent to 0. Therefore, what is the stopping potential for wavelength equivalent to 150 nanometers? Who will tell me? What is the stopping potential? Where happened? What happened to my chat box? Chat box. Ah, yes. Chat box. Yeah. Beautiful. Now I want you at 150 nanometers. What was my stopping potential? It was equivalent to 3.6 minus 3.6. Negative sign tells me that it was negative potential. Magnitude is equivalent to 3.6 volt. Okay. 3.6 volt can also be written. I will teach you the units. Can also be written as 3.6 electron volt. When one electron has a voltage of 3.6, we can also say that the energy is equivalent to 3.6 electron volt. So the stopping potential for 150 nanometers is 3.6, but for 100 nanometer, it was 7.4. So how is the wavelength changing with the stopping potential? Increasing or decreasing? When the wavelength increases, what happens to the stopping potential? When the wavelength increases, decreases. Wonderful, Shivaswamy. Wonderful. It is decreasing. First time it was 3.86. Now it is 1.79. So it is decreasing. The current is decreasing. First, the stopping potential was 7.9. Now it is 3.6. So the stopping potential is also decreasing. For these 4 points, can you just draw the line and tell me whether it is similar to the first line or different from the first line? Plot it. For 0, 1.79 minus 1.5. I hope you have copied down. Plot it quickly and tell me. Plot in the same graph paper. Whichever graph paper you did the first graph, you do the same graph paper with a different wavelength. I'm giving you time. Please fill it up. Quickly, if you draw, you can understand and then study it very easily. And if you don't draw it yourself, you will not learn anything. So please take the pen and plot it. I'm telling you only the first decimal place you plot. I want only but not in your lab. Lab work, you do it carefully. But now just to understand what is happening, I want you to do up to the first decimal place an approximate graph. And tell me how it is. Is the nature of the curve same as the previous one or is it different? There, as the magnitude of the voltage was increasing, current was decreasing. Is it now the same type or different? Same. Very good. It is similar. I won't say same. It is similar. But the current at V is equivalent to 0 has decreased and the stopping potential has decreased. So the curve is similar type but has different values. How the values can be studied, I think you have understood and you told me the answer that when the wavelength was 100, the stopping potential was 7.9. When the wavelength is equivalent to 150 nanometers, the stopping potential is only minus 3.6. So it is going to change. I have now shown you what happens when the wavelength changes to the voltage current curve. Now I will not change the voltage. Let me keep it over here or let me keep it at 100 only. I should keep it constant. What happens if the intensity changes? Okay. So now I will do the experiment we have already done first experiment. We did it for 100 and we did it for 5 watt per meter squared. Now, instead of 5 watt per meter squared, I'm keeping it at 10 watt per meter squared and noting down what will happen to the voltage and the corresponding current. Please check. When the voltage is equivalent to 0, please write on top, wavelength is equivalent to 100 nanometer, intensity is equivalent to 10 watt per meter squared. Previous value, first experiment, we did it for 10 nanometer and 5 watt per meter squared. We will compare those two graphs, first and the third. Okay, so you will write over there all the constants. Lambda is equivalent to 100 nanometer, then intensity is equivalent to 10 watt per meter squared, and then change voltage and note down the current. When the voltage is 0, what is the current? Who will tell me? Current is over here, 7.72. I'm changing the voltage a little bit. Now it is minus 0.8. What is the voltage? It has decreased to 6.92. Now again, if I change this voltage, what will happen? It is 1.8 and the current is 5.92. Like that, I'm going to take this reading. It is minus 3.1 is the voltage and the corresponding current is 4.62. Now I'm changing the voltage. Minus 4.2, current is 3.52. I hope you are writing it with me quickly. I'm doing it quickly so that we can learn many more things. Then it is 5.3, current is 2.42. Are you seeing? Hope you are writing it correctly. 6.5, current is 1.22. Now I will go to 7.3. Current is equivalent to 0.42. I will go again to 8. 8, I'm jumping too much. 6, 9. Okay, now see, I've gone to 7.9 or 7.8. When it is 7.8, the current is equivalent to 0, 0. So what is the stopping potential? I want you to answer, please. I will go to your chat box. Yes, what is the 7.8? When the first experiment we did for the wavelength equivalent to 100, but intensity was equivalent to 5, what was the stopping potential? 7.9, 7.8 are similar numbers. I have not moved it carefully. If I move it carefully, both the numbers will be same. So it tells us now intensity does not depend upon the stopping potential. Whether the intensity is 5 watt per meter squared or 10 watt per meter squared, my stopping potential will remain the same. Did we understand this? Is the stopping potential changing when I change the intensity? No, it was the same. Therefore, intensity does not affect the stopping potential. But does intensity affect the starting potential? That means when the potential was equivalent to 0, then was the current same in both the cases? Yes or no? Current was the same? No. Once current was at V is equivalent to 0, current was 3.86. Now the current was, let me check my readings. It was equivalent to 7.72. Is it same? When the intensity increased, the starting current increased tremendously. First time when the intensity was 5 watt per meter squared, it was 3.86. But now it is 7.72. That means if the intensity increases, the current will also increase. The starting current will also increase. Are you seeing that? How will you know? Plot a graph. First graph, wherever you have kept, keep it. In the same graph paper, take another pencil or a dark red pen and plot this graph. If you plot the graph immediately, you will realize what is happening. Can I ask you to plot the graph in the same graph paper, but with a red ink pen? Red ink pen or another black ink pen. If you have done it with pencil, use blue pen. If you have used blue pen, then use a pencil. something different color, different thing, so that you will understand it quickly. I'm sitting and I'm waiting for you to tell me the answer. Are they exactly same or there is some changes? I want you to draw, please. Decreasing with a different value. Very good. At V is equivalent to 0, is the current same? When V is equivalent to 0, voltage is equivalent to 0, is the current same? Those of you who have drawn the figure, look at the figure and immediately you can say. No, it is not same. Which was more, 5 watt per meter squared or 10 watt per meter squared? 5 was more, 10 was more. For 10 it was 7 point something, for 5 it was 3 point something. Yeah, can you understand that intensity will decide on the starting current? When the intensity increases, current increases. But the frequency or the wavelength depends upon the stopping potential. Stopping potential is a measure of its kinetic energy. Therefore, when the frequency or wavelength changes, the kinetic energy changes. When the intensity changes, the current changes. I want you to realize that. This is called analysis. You look at the graph and you analyze and you give your report, your inferences. The teacher should not tell you. You should find out for yourself what is happening under two different situations. What is changing, what is not changing, and then write the conclusion. Your conclusion should be your own. You have to analyze the graph or analyze the values and then you will give the graph. That is called experimentation. Okay. Now I'm just showing another choice. Now what we did, we changed the intensity, we changed the wavelength and we studied. Now I don't want to change the intensity. Let me bring back my intensity to 5. Let me bring back the wavelength to the same value 100 nanometer and I will change voltage from 0, but I want to change the area of the plate just to show you the variety. Now you can do this experiment for different wavelengths, different areas, different intensity, different voltage current every time. By when you want to study, keep two things constant and change the other one. That is how you can find out the relation. Now I have kept wavelength equivalent to 100 like the first case. I have kept the intensity 5 watt per meter squared like the first case. But in the first case, the area of the plate was 0.1. Now I have made it 0.2. Okay, what happens to the current voltage we will see. So again I'm plotting for voltage equivalent to 0. How much was the current? It is equivalent to 7.72. So let me write it. For voltage equivalent to 0, current is equivalent to 7.72 microampere. Now when the voltage is increased a little, it has become minus 0.6. Current is 7.12. When I make it 2.2, current is equivalent to 5.52. When I make it 3.8, it is equivalent to 3.92. I made it 5.7. Current has 2.02. I will go to 6.7. Current is equivalent to 1.02. I make it 7.7. Current has decreased to 0.02. How every time it is coming to, now it will become 0. So I'm moving very slowly. I should not move it very fast because the zero value is very important. Otherwise, your values will become, yeah. So it is for minus 7.8, current is equivalent to 0. Now look at your first graph and plot another graph close to the first graph. Or you can draw it with another green pen, but I don't know whether you have it. So use another graph sheet. Plot the graph. See what are the differences, what are the similarities. Then you can conclude saying that when this happens, this is what is happening. I want you to, all of you to draw the graph. What are the differences you are seeing? I want you to tell me, please. Plot and match it with the first curve and then tell what is the difference. Because first curve, all the other constants were the same. Decreases. What decreases? What decreases, Vishwami? I didn't understand. Current value decreases for given voltage. There is more difference in current. Yes, Shraddha has told it. Has the stopping potential changed? Look at the two values. Has the stopping potential changed? No. Has the, for V is equivalent to 0, has the current changed? For V is equivalent to 0, has the current changed? Yes. Which current was more? 0.1 centimeter squared or 0.2 centimeter squared? 0.2. That means if the area is large, you will have more current. If the area is small, you will have less current. I am now showing you the FET simulation. Can you see the FET simulation? Yes. If this area, can you see this simulation? What I showed you first, FET simulation? Yes or no? I've lost your, can you see? Yes. Okay. Now in this area, he's talking about this area. If the area is small, less electron will pass. If the area is more electron will come. If the area is still more electron will come. More electron, more current. That is why for 0.1 centimeter squared, whatever was the current was 3 point something. For 0.2, the current became 7.72, almost double. If I make it 0.3, it will become still more. If I make it 0.4, it will become still more. So the current will increase when the area over here increases because more electrons can come out. Okay. So I want you to make your conclusions, make a chart, draw, find out all these relations, do the experiment once again, do it slowly, change it slowly, and then you will be able to understand better. So now what I'm telling you is, how will you go there? Very, very important. I'm showing it to you. Start. You can see the moment I write VLabs, it is VLab Amrita, VLab Physics, Photoelectric Experiment, Amrita Virtual Lab, so many different ways. Which one only you can press? Suppose I want to go to Amrita Virtual Lab answers, I don't want. I want to go to Virtual Photoelectric Effect Virtual Lab. Then when I click over here, there will be a list of things which you can do. Go to Amrita place where vlabamrita.edu, go there. So you will press or click on photoelectric effect. Once you go to photoelectric effect, you will get value at Amrita, etc., etc. Here he has a variety of things. Theory, if you want to learn, theory is given over here. How to do the experiment, if you want to learn, it is given over here. How to perform the experiment. If you want to evaluate yourself, there are some questions, then you have to tick the answer. Is given when UV light is incident on zinc metal surface, few electrons are emitted. The phenomena is called thermal emission, Compton effect, photovoltaic effect, or photoelectric effect. If you click the right one, then the answer will come saying that you know it. If you don't write it properly, then it will say that answer is not correct. So this is how you can evaluate yourself. How much you know, how much you need to learn. This is simulator. When you go to the simulator, that experiment will come. But when you go to the simulator, you can't use it before you log in. Sign in to view the content. So here it says only an authenticated user can view this page. Please log in if you have an account or else sign up. If I'm starting first, I will sign up. But I have already logged in. Sign up means you have to give my password and ID. I have already done. So I will log in. When I press on login, it is asking, what is your username? I have to write my username. My email ID is my username. What is my password? I should not tell you my password. So I will type it. Once I type my password, it will allow me to get in. So I'm entering my password. The moment I finished writing the password, if I say login, it will log in. Once it logs in, that means it is giving you the chance to use the simulation that they have provided for doing the experiment. So it will come over here, photoelectric effect, and the apparatus will show. But I have to use the apparatus. So I'm double clicking on it. Or here, this 3-dot line over here will tell you, choose what is your frequency, what is your voltage, etc., etc. So you will first switch on and then only you can do the experiment. If I finish the experiment, if I do reset, it will come back to its original state. Or if I switch it off, switch it on, switch it off, switch it on, switch it off, accordingly I can click and then I will do. Then I showed you how to do the experiment. You will change only 2 things and keep all the others constant and change something else to compare with each other. Plot graphs and then submit it to your ma'am and tell her that yes, I have finished photoelectric effect. This is my conclusion. When you write the conclusion and write it correctly, that means you have done the experiment correctly and you must draw graphs. After that is over, there is possibility for you to do assignment. He's given so many different things. If this happens, what happens? This happens. So you will do the assignment, you will learn more of it. You want to learn, read more things. Then he will give you a bibliography where he will say, go read this, go read this, go read this. In the library, you will have books, Concepts of Modern Physics by Arthur Beezer, Basics of Quantum Mechanics by Ajay Ghatak and S. Lokanathan. If you have these books in the library, you go to the library, read it for your better understanding. You will understand the theory, you will understand the experiment. Suppose any of this book is not available, go ask your teacher, ma'am, can we order this for our library? She can order it for the library and you can see it in the library, read it in the library, or take it home for 1 week, 2 weeks and read it. If you read, you will understand it better. Then he is asking, there is one column, after having used it, what is your view? Whether it was a good one, bad one, so many different, name the experiment you did, simulator, etc. Then he is giving one table, whether it was good, this was good, excellent, etc. Your feedback is very important. Give your feedback. If there is any problem with the site, then they will correct it. If there is no problem, they'll be happy to get a good feedback and they will keep on improving, doing new experiments every time for students to use it. So it will be good. Now I have told you how to go over there and how to see for yourself. Is there any other questions you want me to answer? Please ask.
Madam, these books are available with us.
Should be available.
Yeah,
All
yeah.
libraries
All
will.
books are there, madam, in
So
library.
sir is also guaranteeing all the books are available. You
Yeah,
can go to
madam.
the library. If you read it, you will understand it better. Then
Yeah,
you will be able to do everything in theory and practical very nicely.
Yes,
Okay?
madam. Yes, madam.
Yeah. Anything else you want to know from me, please tell.
Yes.
But nothing you need to know from me. Everything is there in the net. You can simply scroll through and study.
Yes.
If you pay attention, I told you, no, learning is done by yourself. Whatever I say or don't say, if you don't want to listen to me, you'll put one cotton in your ears and sleep. I cannot help. But if you want to learn, you will go and analyze for yourself. You will go and find out for yourself and you will learn better. So learning is done by yourself. You should have the motivation. You should have the inclination. You should have the Josh for learning. I want to do it. And therefore you should learn better. You will learn better. Okay.
Madam, now I request students to interact with you
Yeah.
about all the 3 sessions
Yeah.
and also some questions regarding the 3 sessions.
Yeah. So shall I
Now,
close one thing? I'm going back to my PET
yes, madam.
simulation want. I will go back to my face being
Students are
visible.
requested to raise the hands.
Sharing.
I will unmute themselves and so that you can interact with the resource
Right.
person.
Now I'm ready.
And you can give the oral feedback also.
Yes, please.
Students, Shraddha, Meghana.
So some of them are very, 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 very interactive and I'm
Yeah,
liking
madam.
it. They are immediately answering.
Yeah, they're active participant, madam.
Yes, yes.
Yes, students, please raise your hand so that I can unmute yourself and you can speak with madam orally.
Yeah, and I would like to take a picture of you all. So if you can show me your video, audio,
Madam.
then we can take a picture. Or sir, you will only take it.
Yeah, madam, I am taking, madam.
Yeah.
Please, students, unmute yourself, all of you.
You can unmute. You can also show your videos so that we can have a look at you. Oh, the room is having so many children. Shushma Jiddar. Yeah. Okay, excellent, excellent. Dayanand, Pandu. I think we have exceeded the time.
No, madam, no.
Oh, no problem. If the children are interested, they can continue.
No.
Otherwise,
Yes, madam, I have taken the screenshot of this.
okay. Thank you. Pandu, you are asking something. Which video you are asking of?
Madam, let me
Unmute them.
unmute.
That will be better.
Pandu.
Yeah.
Pandu, you unmute yourself and ask to the madam. Pandu. Pandu, speak now. Hello.
Unmute yourself, beta. Unmute yourself and ask.
Pandu. Hello.
ನನ್ನ ಮನೆ ಕೇಳ ಏನು ನಿಮ್ಮ ಮನೆ ಫೋನ್ ನಂಬರ್
Okay, madam. I think he is not interested.
Okay. Okay.
Any other else?
For some video, I don't know, understand what. Okay. Anyway, if there is any question, if you want to ask any question, you are unmute yourself and ask. The field, the whole day is too long. We will stop now. Don't worry. Don't worry. Since it is becoming a very long session, we will close it in a few minutes. If you have some burning questions you want to ask, ask. Otherwise, I've given you my email. Please send your feedback or questions. I will answer. I have given you one link for a Google form for the feedback. If you fill it up, I'll be very happy. But if you don't want to fill it up, also fine. If you spend some 2-3 minutes, you can fill up the video. It will be of great help to me to take the feedback for my further studies. But if you say, no, I don't want to feedback, it's fine. No problem.
One notice, the students are requested to fill the feedback form so that they may get the certificate of the workshop.
Okay.
And it is mandatory to fill the feedback compulsorily.
Okay.
And we are providing you the feedback link in the chat box as well as in the group.
Yeah.
We have created the two group, madam.
Okay. Then you can send the link to them.
Yeah,
them
sure.
Fill it up, and based on that, you can give them the certificate. No problem.
Okay. Immediately that certificate will be sent
Once
to
they
them.
submit, I will get the feedback in my Google form.
Yeah, sure, madam. Sure.
Yeah.
Sure.
Thank you very, very much, sir.
Madam, let me conclude. One
Yeah.
second.
Yes.
Second. Now I request Bhavani to take over the session.
Thank you so much, ma'am, for your priceless and wonderful sessions. Now we have come to the end of our session. Now I call Ms. Sridevi to propose the vote of thanks. A very good evening to all of you. It gives me an immense pleasure to deliver a vote of thanks. For a Samyuktha Sahu madam with her knowledgeable event to all the students, dignitaries assembled here. I would like to thank our respected resource person of this session with her inspiration thoughts about the solid angles, simulations, and a virtual lab, which is knowingly unknown to us, as all sessions were very interactive and make us knowledgeable. Thank you, madam. Thank you so much for your knowledgeable informations. I would like to thank our principal, Dr. L.D. Horkeri sir, HOD of the Physics Department, Dr. P.R. Jirgal sir, staff members, students, and all the participants, organizers, and the volunteers. And last but not the least, our beloved audience for making these sessions very grand success for this function. Thank you, ma'am. Thank you so much.
God bless you. God bless you.
Thank you, ma'am.
Ma'am, now I'm sharing the link. Please, all the participants request you to fill that one kindly. Thank you so much for all of you for participating and making this grand success. And thank you very much, madam. And our
Thank you
students
very much
are
for this wonderful
very happy
opportunity.
to hear you, and their knowledge is enhanced. And thank you very much, madam.
Most welcome, sir.
Thank you, madam. Thank you. Now I will conclude, madam.
Yeah.
Thank you. Thank you.
Yeah. Shall I leave?
No, madam. I will send the link now.
Yeah. No, say link you
Thank you
sent.
so much,
I
ma'am.
don't have to be here.
Madam,
Okay.
Dr. Veena is speaking with you, madam. Dr. Veena.
Okay. Yeah. Yes, Veena.
Thank you so much, ma'am.
You're most welcome. Thank you for giving me this opportunity, wonderful opportunity to talk to your students, to interact with your students. And it all happened because of you. So
Thank
you
you.
are the main person for everything, for organizing everything, for collecting, getting permission from your principal, everything, setting it up. Wonderful. Thank you very, very much. Keep going. We can have some more workshops, maybe small groups, so that they can really learn step by step.
Yes, ma'am.
Okay.
Thank you.
Right.
Thank you so much.
Thanks a lot. Thank you very much.
Bye, ma'am. Thank you, ma'am.
Bye-bye. Bye-bye. Bye, sir.
Thank you, madam. Bye.
Madam.
ಮುಗೀತಲ್ಲ
Pinri.